Sushruta for NEET is now available on the Google Play Store. Try it out for free.
Welcome students to our JnanaMarga presentation. We are looking to discuss today the mechanical properties of solids, and it is part of the idea of mechanics. So the important material that we first look to teach is also study methodology. Now, JnanaMarga has a different study methodology compared to many other programs. Okay, we bring in IIT PAL into your ebook. And so the study methodology uses the best of breed technology to allow students to read books, view slides, and watch videos all from one integrated viewpoint. And so this is our core technology. Now we offer this key technology to students using our two flagship trademarked platforms. The first is Sushruta for the NEET students, and it is available for a free download. You just have to go to a Play Store, get it on Google Play, go to Play Store and look for com.jnanamarga.sushruta. Okay, com.jnanamarga.sushruta, SUSHRUTA. Okay. Now, once you look for our app and download it, and install it, right? There are 2 weeks during which it is free. After that, what you can do is you can register. Actually, you should first register right away. The first thing you do is you download and right away register. Okay. Then after 2 weeks, you do not have to buy, but you must try. Okay. Try and then buy. But if you miss the 2-week window, then it becomes trickier for you because you don't know how good it is and whether it is suitable for you and how it can help you. So that is very, very critical. Our Sushruta for NEET integrated learning platform comes in two forms. One is through this app download, which is from a cell phone. The other is through our tablet platform. Our tablet platform is among the best and most affordable in the industry. At 25,000 rupees, students will get a full tablet along with the H.C. Verma textbook and many different, a couple of additional books in the case of Sushruta, and you will have the full integration for physics, chemistry, and biology. Along with that, our live lecture series. I am your physics teacher today, but we also have two PhDs who work with me. One is Professor G.K. Bhatt, who is a famed teacher for biology and among the best in the business. Most of his students excel. Many of his students excel in biology in the NEET. Okay. Then there is Dr. Tiwari. Dr. Tiwari works for National Chemical Laboratories, but is a dedicated and wonderful teacher. Working with Dr. Tiwari will teach you so much as he introduces chemistry as a subject to various students. Okay, and along with that, we have additional modules as well, which come with like our chat module, etc. Okay, so these are all part of the overall program that we provide. Our second flagship program is Ramanujan, our trademark Ramanujan app for JEE students. Ramanujan is also among the best in the business. It also comes with H.C. Verma as an ebook if you buy the tablet, and then the C-Engage book for maths, and then Solomon's for organic chemistry. Okay. So this is for the tablet students only. The students who just download the app, they get the same thing as Sushruta for NEET. You download the app and you immediately register. You get 2 free weeks. You can try out the app and then you can go forward. These lectures are also free. You're free to attend these lectures. We take pride in teaching every student. Okay, and so all our platforms come with slides, and they come with linked with live lectures, and and also now we provide the Jnana test prep, which is our assessment module. In both Sushruta and Ramanujan, you will find that you can take self-assessments, and we are rapidly working towards our own assessment as well. So the self-assessment allows you to go to other sites and take questions right now, and very soon you will have also our own assessments available through these apps. Okay, now let me take the next step. Okay, rigid and which is get on with the business of the day. Okay, now we see many kinds of solids, right? For instance, this is my mask. You can see that my mask extends a little bit. It is made that way. It is soft, and it is deformable, and it is made of cloth, so it kind of folds, and you can do many things with it. Compare that with my spoon. Okay, my spoon is a very rigid body, but when you subject to it to great force, it will also bend. Okay, now but it will not. It is made to bend, but not break. Okay, so all these are properties of various solids as well. So far, when we studied mechanics, we talked about rigid bodies which don't change their form. They're not deformable bodies. But here we are discussing bodies that are at least partly deformable, temporarily deformable, and also forever deformable too. Okay, so when force is applied, there is a deformation, right? The object is called plastic. Okay, when force is applied and the body regains its original shape, then we say that the body is elastic. Okay, now this idea around deformation is extremely important in civil engineering, design, and construction. Every bridge, right? A lot of the bridges are suspension bridges. When I started studying when I went to study in IIT, in the first class we had of engineering, or one of the first few classes we had of engineering mechanics, the professor for engineering mechanics, he discussed the Manhattan Bridge, which is a suspension bridge, and it is held by these extremely strong steel wires, and they hold up the whole bridge. Steel has tremendous properties of both being somewhat malleable, but of great strength in that it doesn't break. So these thick, they're probably this thick, and there are many of them though, but with a few of these thick steel wires, they're able to hold up a whole bridge and have 24-wheelers, cars, trucks, etc. go freely across these bridges. Okay, of course some also have vertical support, but this is what holds up several of these bridges, and it is an amazing thing that as to what is achievable by learning about elasticity. Okay, so having moved on, let's now look at the idea at a more interatomic level. Inside a at the very depth, you all know that gases have few molecules which kind of move around, right? Now, the interatomic forces in a solid are extremely strong. Towards the end of your class 12 material, you will learn about this interatomic forces, and you will learn how bodies, how these interatomic forces hold things together inside, different types of materials, and so you will see this very same diagram discussed in greater detail. Okay, so when there is, there is a beyond a certain distance, there is, there is a different kind of force that comes into play. Okay, so these interatomic forces are very central to our to how materials behave. Now solids behave like an like elastic balls on springs. If you push them, they will typically, some of them at least, will deform. Okay, if you remove the force, they will come back to their original shape. There are, that is like elastic behavior. Okay, so they will, if you pull them, they will proportionally elongate. But then you must note that in certain cases, this elongation is coupled with a shrinkage of the material's width. Okay, so it becomes a little thinner but longer, right? Now, what is the one law that you should learn with respect to how elastic solids behave? Okay, and this is very specifically elastic behavior. Okay, elasticity happens only under certain circumstances, not always. We already discussed that. Under certain circumstances, there is no elastic behavior. There is plastic behavior. Okay, so now when elastic behavior happens, there is a linear law called Hooke's law, which occurs within a range of applied force, beyond which it does not return to its original shape. Okay, instead it undergoes deformation. I'm sure all of you have underwear. Underwear, you will find that normally it will fit tightly when you buy a new underwear, but after some time that elastic just stretches and stretches and stretches, and it is no longer coming back to its original shape. So think of it in using that. Okay, so, and we do call the top of the underwear an elastic. Now, the next idea that I'm going to discuss here is this idea of stress. Okay, stress is defined as the force per unit area. Typically, when we discuss stress and strain, we don't discuss too much like vector rotation. It's not discussed that much with vector rotation. Think of a linear rod. Think of it being stressed, right? The area is, cross-sectional area. Okay, so now stress is like, there is the other thing that is force per unit area is also pressure, right? When we discuss the term pressure in physics, we also talk of force per unit. Similarly, stress is also force per unit area, albeit we deal with it only in the context of solids. Okay, so while pressure, very often we think of it in the context of fluids, be they liquids or be they gases. Okay, so now when we think of solids, we have this term called stress. So when a body is subject to a deforming force, an equal and opposite restoring internal force called stress develops. Notice the definition of stress. Okay, it is a restoring force inside. It's an internal force, and it develops, and its aim is to restore the object to its original shape. If the object is stretched, it is called tensile stress. You know, as I mentioned, the steel in the context of the bridge, right? Steel has tremendous tensile strength. You know, it is probably why it became the king of all materials. But of course, it comes in so many different forms of steel. There's cold rolled steel, different types of steel. You know, now why did it become the king of all materials? Well, you know, you might have heard of Bronze Age, right before what is today called the Iron Age. You know, in many Indian languages, we say Kali Yuga. You know, Kali Yuga is the equivalent of Iron Age. You know, and so if an object is stretched, it is called tensile stress. If it is compressed, it is called compressive stress. Okay. Now, what is the magnitude of stress? The magnitude of stress is measured in terms of the force per cross-sectional area. The force, let's say you have a string like this, the force is what is what is applied at the ends to pull it. Okay, and the stress occurs to bring it back to its original shape. Okay, now the area is a cross section of what is being stretched. Okay, so let me find something. Okay, here is my this. Okay, so now if I look at this one, the force that I am applying is the stress. I am applying stress on this. The amount I am pulling is applying, it is causing tension here, and it is applying stress. Okay, it's applying force. External force is tension, right? So now internally, the body, that is this ribbon, is experiencing stress. The stress stretching slightly. Okay, now when I let go, it returns to its original shape. You might try it with a rubber band, right? Now the area is the cross-sectional area of this. You know, so this might be maybe 1 millimeter by about this is probably 3/4 of an inch, maybe 2 centimeters. This is my guess. Okay, maybe 2 centimeters by 1 millimeter. Okay, so what is the area? 2 times 0.1 right, centimeter to millimeter, 2 times 0.01 maybe, you know, 2 times 0.01 would be the area. Okay, so in cm square. Okay, now the force per unit area is the force that I applied, measured in newtons, divided by this area that we came up with. Okay, so now that is stress. Now the other term is called strain. Okay, strain is the extension of the body, and this is called longitudinal strain, is the extension of the body to its original length, the level of the extension to its original length. Okay, so let me try this one. So this one stretches. You see, this is a very elastic material. So when I pull it, it really stretches, right? So now when I pull it more and more, it keeps stretching. Then it returns back to its original shape. Okay, so we say that this is the the level of from which maybe it was 2 centimeters, now it has become 3 centimeters. That is your delta L. The original length is 2 centimeters. That is your L. So the longitudinal strain is the extension, which is of course about 2 centimeters, divided by the original length, which is about 2 centimeters also, or maybe 3 centimeters, whatever that length was. Okay, so the increase in length divided by the original length is the longitudinal strain. Longitudinal strain has no dimensions, while stress has a dimension force per unit area. Now, stress divided by strain over a period of, over a certain force, you know, per unit area remains, is a straight line. Okay. So if you plot stress versus strain, and this is what Young's modulus is all about. Okay. Now, there is another idea which is called shearing strain. Okay. So this is when if there are two opposite forces not aligned, and we're not pulling like this or pushing like this, but we are pushing, we are producing what is called a shear. Okay. I'm pushing here, I'm pushing here, I'm pushing here. The two sides, they kind of shear against each other. Then we say that we talk of what is called the restoring force produces what is called a shearing strain, okay, which is the amount of delta x divided by L. Okay. Now, in the case of hydraulic compression, okay, hydraulic compression is a very important idea. It is used in many different places, most notably in brakes. You have what is called a hydraulic brake. When a fluid inside a body looks to press back at a perpendicular force, the stress produced is the applied force, right? At a perpendicular applied force, it is a hydraulic stress or hydraulic pressure. Okay. Now, what then happens? So you put a lot of pressure, it faces hydraulic pressure, and it also pushes back, because fluids like liquids, right? They also retain volume. They may be flowing here and there, but the volume stays. When you remove the pressure, the volume returns to its original volume. Okay, there is also a restoring force there. Okay, what causes it to return? Restoring force, right? Doesn't become ice or become smaller and stays like that. Okay, now the strain that is produced though is a volume strain. Okay, when you apply a force, the volume goes a little bit shorter, lesser. So the change in the volume divided by the original volume is what causes hydraulic compression. Typically, we mainly deal with hydraulic compression. Okay. Now let's come back to Hooke's law. Okay. So this is a slight aside, but now we are coming back to what we were discussing before, which was this stress over strain, right? So for small levels of stress and strain are proportional to each other, and in that phase when it completely recovers back to its original shape, right? So there is a straight line relationship between stress and strain, and the slope of that y equals mx curve, the slope of that y equals mx curve is k, right? So more the stress, more the strain, right? Or more the and so the stress versus strain curve, stress is plotted on the y-axis. The slope of that stress versus strain curve is called K, and it is called the Young's modulus. So the ratio, and they use the term Y. The ratio of the stress to the strain, stress is typically the notation for stress is sigma, and for strain is epsilon. Okay, so sigma by epsilon is a linear relationship, and that value is called Young's modulus. It is different for different elements. Okay. Now let's look at the stress versus strain curve. Okay. So now this portion from here to here, the stress versus strain curve is a straight line. Okay. Then there is a phase. Okay. And after A, right, linearity disappears. At this point, linearity disappears. Okay. At B, it ceases to regain its original shape. Okay. Now at E, there is what is called fracture. Okay. The point D, this point on the graph is the ultimate tensile strength of the material. So after that, it's going to be start giving up. Okay, if D and E are close, okay, these two are close, this and this, then it's brittle, so that it reaches that part, it will break, but sometimes it will extend and it goes through this process called necking. Okay, so there is deformation starting from point B. Okay, so A, B, D, and E. Okay, so A up till A, there's linearity, right? From here to here, linearity. At B, it is the point where after which it doesn't regain its original shape. Okay, this point is called the yield strength. This is the maximum at which the body will completely regain. It's the maximum force you can apply at which you can completely regain its original shape. Okay, so that is yield strength. Okay, so so K is called the slope of this line is called K, and it is called the modulus of elasticity, or Young's modulus. Okay, now elastomers, that's this. Elastomers are very stretchable material. Okay, so when it is stretched, when it's stretchable, right, starts here and I can make it as long as you want. Rubber and the tissue of the aorta is a vein in the heart. Okay, the tissue of the aorta are considered elastomers. And I say this, hopefully you will remember when you all become, or at least some of you become doctors, you will remember, yes, I remember, So the rubber, and of course, I don't mean to say that some of you engineers will not be making rubber. Okay, maybe some of you will go on to make rubber as well. So, so whether you are making rubber or a cardiologist treating heart patients, remember, that both are elastomers. Okay, very stretchable material or tissue which can stretch a lot but completely regain their shape. Okay, so sigma over E is called Young's modulus. It is F by A is the stress, delta L by L is the strain. So sigma is F by A, delta L by L is epsilon. Okay, so sigma over epsilon is Y. All right. Okay. A copper wire of length 2.2 meters and a steel wire of length 1.6 meters, both of diameter 3 are connected end to end. This is a very, very common question dealing with Young's modulus, and you should be able to get 100% in all these questions. Okay. When stretched by a load, the net elongation is found to be 0.7 millimeter. Obtain the load applied. Okay, so you have to look up the Young's modulus of both copper and steel. Notice the Young's modulus of copper, 1.1 into 10 to the power of 11. Notice steel, twice copper. That's why we went from the Bronze Age to the Iron Age, or if I may say, Steel Age, 2 times 10 to the power of 11. Okay. Now, so having said that, the Young's YC, right, is the common load, right? Let us call that W. Okay, the common load, let us call that W. W by A divided by delta L over L equals YC. Okay, so now W over A, right? We are saying they are connected end to end, both of the same diameter. Okay, so W over A remains constant. So y times delta L over L will be the same for both. So YC times delta LC over LC equals YS times delta S delta LS over LS. Okay, so this is the key equation here. Okay, but you do know that delta LC. So what are all the unknowns here? Right? LC is a known. LC is this. LS is a known. LS is that. There are two unknowns though. YC we looked it up in the table. YS we looked up in the table. Now, what are the two unknowns? Delta LC and delta LS is an unknown. But delta LC plus delta LS equals 0.7. Okay, so you have two equations, two unknowns. Delta LC divided by delta LS, right? So in this equation, this is a known, this is a known, this is a known, this is a known. These two are unknowns. So you have A by B equals something, A plus B equals something else. Solve for A and B. Okay, so then you solve the two equations, two unknowns, and you can just solve for it. So just say you put DLC equals 7 minus DL. So DLC divided by 7 minus DLC equals 2.5. And then it's a simple linear equation. Cross multiply, and it ends up being a very simple linear equation. You can get DLC and then correspondingly DLS, he gets 5 and 2. Okay. Once you get 5 and 2, then you can solve for the W and A. How do you get the A? Pi r square. Okay, so copper wire has with a diameter of 3, that means the radius is 1.5, pi times 1.5 square. Very simple. Okay, so these things are very simple. They match exactly what you have learned. Okay, so now how do you determine in a lab experiment Young's modulus? Okay, so how do you do that? You have two wires. Okay, now you have a reference wire on the left side A and a experimental wire on the other side B. Okay, now you keep, and both wires are assume that they have the same thickness, right? And we can measure the two lengths, okay, with the two unstretched lengths, right? Then we suspend them. Okay, now we look at the change in the we also use like a vernier calipers. I don't know if you all heard of vernier calipers, but it's a way to measure the diameter. Okay, using the diameter, then divide by 2, get the radius, pi r square will give you the area, right? So now mg by pi r square, you add known weights here, mg by pi r square, right? Now, and as you add weights, right, why do you need that? Okay, you need that because you don't know the weight of this pan, right? You try to keep identical pans. Okay, now when you keep a weight in this one and when you keep a weight in that one, then it correspondingly both will stretch, and based on the differential extension, you can then say the incremental weight that I applied led to this kind of incremental extension. Okay, so you start with the same weight. You say, okay, now I started with the same weight, right? Now, when I increase weights on this one, it has gone this much more, this much more. So the increase in weight to the increase in length is what you're measuring. Okay, so that is the basic idea in and what happens in the experimental wire. It should, you note the reference when they both have the same weight, okay, and then each additional weight that you're adding is going to, it is exactly that. Let's say you add 2 kilograms, the extension is exactly for that, corresponding to that 2 kilograms. Okay, so that extension is what you're measuring using this vernier. Okay, and so that extension will give you the delta L. We already measured the original L. We already got the thickness, etc. Okay, and therefore mg times L by pi r square times delta L. You keep doing that again and again. You will get various values for the Young's modulus. Each time you add some more weight, you will get a different extension, various more values. Hopefully it will give you a sweet straight line as you keep adding weights. And at the point when it starts to not be a straight line, that's when you start talking about yield strength, etc. Okay, so so with that, let me do a couple of problems, because we already did one problem. Let us do one more. One end of a horizontal thick copper wire of length 2L and 2R is welded to another end of a horizontal thin copper wire of length L and R. When the arrangement is stretched, notice that both are copper. When the arrangement is stretched, what does that mean? They both have the same Young's modulus. When the arrangement is stretched by applying forces at two ends, what does that mean? The net force is the same across the wire. Okay, the ratio of the elongation in the thin wire to the elongation in the thick wire is, okay, so F by A divided by delta L by L, right? The F is the same, the Young's modulus is the same, given F and Y are the same. The only things that are changing are delta L, L, and A. Now, delta L is the unknown in each case, right? A and L are knowns. In one case, A is pi times 2r the whole square. In the other case, it is pi times r square, right? Therefore, when you and in one case the L is twice, in the other case the L is L. Okay, so now the ratio of the areas will be, the area ends up in the denominator, right? Therefore, A1 delta L1 by L1 equals A2 delta L2 by L2, right? So delta L1 by L2, right? So which is the delta L2 by delta L1 equals L2 by L1 times A1 by A2. L2 by L1 is 2, A1 by A2 is 4, or L1 by L2 is 2, A1 by A2 is 4, right? So 4 divided by 2 is 2, right? 4 divided by 2 is 2. All right. So similar question, another one. Okay, 1 kg mass is suspended from a wire of negligible mass. So let me discuss briefly the negligible mass. Right? Why do they say negligible mass? It's because they want this idea that if it has some mass, then the tension across the wire is changing a little bit, But if it's negligible mass, you don't have to worry. You can say the tension is uniform across the wire. Not that it's a big deal. Okay? The length of the wire is 1 meter and its cross-sectional area is 4.9. If the mass is pulled a little in the vertically downward direction, released, it performs simple harmonic motion of angular frequency. They are saying, think of the wire as a spring. Okay, if the Young's modulus of the material is N, okay, the value of N is what? Okay, so now what is it performs simple harmonic motion of angular frequency 140 radians per second. Okay, so now let's look at this. Okay, so in simple harmonic motion, what happens? Mg, the force, is equal to basically kx, right? Force is kx. Mg equals kx, right? And and correspondingly, you find that 2 pi times square root of m by k is what? The period, right? Omega square equals square root of m by omega square equals m by k, right? So kx equals ma, right? So now k over m is omega square, right? K over m is omega square. So k over m equals 140. Now Young's modulus of the material is what? Young's modulus is the stress by strain, right? So now how is that related to the K, right? So Young's modulus, F equals Kx, right? But F is not what you're interested in. You're interested in F by A divided by X delta divided by X by L. Okay, so you must add those terms in. Okay, so omega square equals what is that? K over m. What does that give you? Right? Omega square equals K over m. That is used to calculate the, because you know omega 140, right? You know m 1 kg. That is used to calculate the K. Okay. So now you know F equals Kx, right? Now what is F? 1 times 9.8, right? And so 1 times 9.8 equals K times X, right? But then what you're interested in is not K, you're interested in Y, right? So how is Y related to K? It is F divided by A divided by X divided by L. So you have to divide by the area. The area is pi r square, or not pi r square. Area is given to you 4.9 10 to the power minus 7, and you have to multiply by the length, which is 1 meter. So when you factor that in, you will then get a value for the Young's modulus. Okay, and so from that he gets Young's modulus n equals 4. Right? Not so straightforward, is it? Because he introduced simple harmonic motion. Okay, you needed to know about simple harmonic motion, right? And also remember that this stretching, what he's telling you is stretching is also going to cause it will oscillate like with simple harmonic motion, right? Because it's also a stretching force. F equals kx. Okay, so it's also like a spring in some ways. That's what he's telling you. Okay, so now we move on to shear. Okay, shear is the similar to longitudinal stress and strain, which produces Young's modulus. Shear is the force is is like this. So you're applying two forces, F1 and F2. Therefore, the material elongates like this. In this way. Now, when it elongates, you have the area stays the same, but its length is cross-sectional growth. Therefore, it increases at at an angle. Okay, that increase in the angle is delta. Okay, so a square slab of 50 centimeters and thickness, side 50 and thickness, so it's a square, right? 50 by 50 square, and then it has a thickness of 10 centimeters, is subject to a shearing force, okay, on its narrow face of 9 into 10 to the power of 4 newtons. The lower edge is riveted. So one side we are pushing, the bottom is held. How much will the upper edge be displaced? Okay. So now the upper edge is going to push delta L, right? So the stress applied is 9.4 into 10 to the power of 4, right? Divided by the area. The area is 0.05 square, right? And therefore, or the area is not 0.05 square. It is 5 times 10, right? So the length is 5 and that length is 10. So it is 0.05. Okay. So 50 centimeters by 10 centimeters, that is 0.5 by 0.1, that is 0.05. So area is 0.05 meters square. Okay. So the stress is 9.4 10 to the power of 4 divided by 0.05, and the strain correspondingly is delta x by L. Okay. Now delta x we don't know, the L we know, right? The L in this case is 0.05, right? So given that, you then have the G is 5.6 into the 10 to the power of 9, right? And therefore, using that, you can then calculate the delta X, the shearing length. Okay. Now, with hydraulic strain, right, we talk of this thing called, not of Young's modulus, but of this thing called the bulk modulus. The bulk modulus is the pressure divided by the volume strain. Volume strain is delta V by V. The equivalent of the equivalent of stress is pressure. So pressure by volume strain it will give you the bulk modulus. Okay. Now, if you are compressing it, that is when you have hydraulic strain. If you're looking at compressibility, that is 1 over the bulk modulus, therefore the corresponding inverse of the same thing. Okay. So it is the strain over P. It's called the compressibility. The average depth of the Indian Ocean is about 3,000 meters. Calculate the fraction of compression delta V by V of the water, given that the bulk modulus of water is 2.2 into 10 to the power of 9. Okay, so delta V by V of water equals the bulk modulus equals F. So there is 3,000 feet of pressure, 3,000 times G, right, times 3,000 meter of water on the bottom layer, 1,000 kg per meter cubed, right? 3,000 meters times 1,000 kg per meter cubed times G is the force, right? And the force, or is the pressure, So that pressure divided by delta V by V equals the corresponding bulk modulus of water, 2.2 into 10 to the power of 9. Okay, so from that you end up with delta V by V equals the result. All right. So with that, the final idea deals with Poisson ratio. Poisson ratio is the ratio of the lateral strain to the longitudinal strain. Okay. So how much lateral strain does something experience as opposed to the longitudinal strain? Okay. And finally, the work done is, so we did sigma over epsilon is the Young's modulus. The work done is the energy that is stored in the form of elastic potential energy is sigma epsilon by 2. Okay, sigma epsilon by 2. So half sigma epsilon. Sigma over epsilon is y. Sigma epsilon by 2 is u. All right. So with that, I'm going to conclude, and I will see you all again next class. If it is Saturday morning, it's time for physics for class 11, and we will continue with the material as we move forward, mechanical properties of liquids, and then we will go on to follow on additional material as we move forward with the class 11 material. All right, with that, I'm going to close, and I will see you all again next time.